Welcome back, ladies and gentlemen. We've only got a little bit left to cover, and today I want to start by covering it with this. You've probably seen this before. It's called Newton's cradle, named after that Newton guy that we spent a whole bunch of time talking about last time. And a Newton's cradle is a desk toy. It wasn't actually invented by Newton. It was just named after him because it relies on Newton's laws to work. So what we see here is, of course, for those who haven't seen this before, you lift one side and off it goes. Now, if I were to ask you guys to describe what this looks like using forces, you probably could. You could say, okay, so when I lift this up, I'm applying a force, an unbalanced force, so it's going to move. That's first law. And you can figure out the mass of this and see how much it's accelerating to figure out the forces involved, but that's a lot of math, so we're going to skip it. And then when I let go, you know that this is going to swing down and it's going to hit the ball. And when it hits the ball, the force is going to be transferred through until it gets to the end, and then the force will kick this guy off on the other side. And so you get this. And that all makes sense. Until the diabolical Mr. C does this. I'm holding one on either side. Well, if both of these are going to apply a force going in opposite directions, surely that means that they're going to cancel, right? Because a balanced force means there's no motion. But take a look. Madness. This is what we call in physics a discrepant event. It is something that doesn't quite make sense, not as it is. Somehow the force of one ball bearing is passing through the force of the other ball bearing with no appreciable change, no real difference. Other weird things that Mr. C could do. What happens if I raise 2? Well, each of them is going to apply a force, so there's sort of 2 possibilities. 2 could come up on the other side, or 1 could come up but twice as high because it's got twice the force. Let's try it. We lift it up, we let go. 2 to the same height. Crazy. But it gets better still. What happens if I do this? 1 on one side, 2 on the other. What could possibly happen? Well, let's break it down, right? Always break a problem down. 2 turned into 2. 1 turned into 1. So if I've got 2 on one side and 1 on the other, I should get 2 and 1. 2 and 1. 2 and 1. Let's see. What's this going to do? 3 and 2. Yeah. 3 and 2. 3 and 2. Although it's not what it's going to look like. Take a close look. It just looks like the one in the middle is switching sides all the time, but really we know what's happening. 2 come in, 2 come out. 3 come in, 3 come out. So what is this showing us? This isn't forces, and yet it's named after a chap called Newton, who was all about forces. Well, let's see if we can explore this. Turn to your booklets. We're going to take a look at page 66, and we're going to talk about something called momentum. So momentum is mass in motion. Mass in motion. With this Newton's cradle, we very clearly have masses. These ball bearings are masses, and they are very clearly moving. So that means they have something that physicists call momentum. But what is momentum? What does it do? How does it work? Well, you can think of momentum as like an energy. If you've got momentum, you're moving. If you don't have momentum, you're not moving. It's very simple, right? We saw cases where you could have a balance of forces and you don't move. But with momentum, all that ambiguity, all that weirdness goes away. If I take an object and I set it to moving, it has momentum. The moment that it stops, decidedly off camera, that means that the momentum is zero. So the weird thing about momentum is that you can't really get rid of it. I can't just like go make momentum disappear. I have to transfer it. I have to move it from one place to another. So in the case of the tape, when it rolled on by, the momentum was transferred from the tape to the table. And you know this, right? Like if you take your two wonderful hands and move them, what happens? You get warm. Why? Because the momentum is going into your skin, causing it to heat up. Now, there's a little bit more to it, and we'll talk about that after we understand momentum in a little more detail. But the key thing is that momentum means something is moving. And if you remove the momentum, the thing stops moving. Now, the equation for momentum is P equals mv. Now, P stands for momentum. Why don't they use m, you ask? Well, because there's already an m in here. We don't want mm because it would be confusing. So mass is for m, and velocity is v. So it's a very simple equation, thankfully. So how would we use it? Well, let's say that roll of tape there. Let's pretend that roll of tape weighs 1 kilogram. We'll keep it very simple. So 1 kilogram times, it wasn't really going very fast. Let's say it was moving at 2 meters per second. So the momentum in this case would be 2 kilogram meters per second. This momentum tells me how fast it was going. Now, this momentum is just sort of the total energy it has to move. Back to our Newton's cradle, remember when I lifted up 2 lifted up on the other side. Why? Because when I lift 2 and then let go, gravity causes them to move. Gravity provides an unbalanced force. And there's enough momentum in 2 ball bearings to move 2 ball bearings. So instead of 1 flying out, 2 moves. Because that's how much energy I gave it. Heck, I could even do 4. So, the amount of momentum can move a certain amount of material. Similar. Okay, let's say I give this much momentum here. Like, look at this. I got 2 momentum. 2 kilogram meters per second. Applying that to the roll of tape makes it move. No problem. But what happens if I apply that same 2 meters per second to a heavier roll of tape? Oh. So this weighs more, it has more mass. So if the mass is bigger, but I use the same amount of momentum energy, what happens? Well, let's take a look here. Let's say this one is 2 kilograms. Let's say that this second roll of tape is 1.5 kilograms. Let's just, is that a nice round number? Not really. But, you know what, we'll make it a round number. We'll just say it's 2. Right, so we're going to say that this one here, the heavy-duty duct tape, is twice the mass of the masking tape here. So when I give them both a push, they're going to roll at different rates. So what do we get? Well, what we're seeing is the duct tape is slower. And that makes sense, because look, 2 times what number would make that 2? Well, this has to be 1 meter per second. So if I give the 2 rolls of tape the same amount of energy, because they weigh more, because they have more mass, the slower one, the heavier one, goes slower. This is the reason why heavy things are slow, right? Like if you've got a car and a truck, like a big semi-truck, The two of them could have exactly the same engine, but the truck has to carry a much bigger load. So it takes more effort to get up to speed. That's why your truck waiting at the stoplight can't accelerate very fast, can't zip ahead. This is also why a train, when it sees someone on the tracks, can't stop. The train is so big, it has so much momentum, that if it tries to stop, it won't have enough time. It'll try to stop, but it's got so much energy that it needs to get rid of in order to actually stop that it can't. But how do you get rid of momentum? Well, momentum is usually paired with something else. If you guys flip over, page 67 has some momentum questions you can try, just some very simple calculations. Page 68 talks about the twin to momentum, which is impulse. And impulse is J equals Ft. Why do they use J for impulse? I got no idea. They could use I in this case. There's no other I's being used, but they don't. So sometimes they make sense, and sometimes physicists are a little crazy. So impulse equals force times time. Think about it like this. I've got these two rolls of tape, right? And they were rolling along, and you saw that they eventually came to a stop on their own. Why? Because friction is pulling them back. Friction is trying to slow them down. But you'll notice that I managed to go from here all the way to that marker box. But what happens if instead I end up with the marker box a lot closer? Oops, and I run them into each other. I set them rolling, and this guy here hits the marker box. Instead of getting all the way there, it stops early. You'll notice that when it hit the markers, all the markers went shake a little bit. Maybe the marker box shifted a little bit backwards, not too far because it's got some nice rubber padding. If I use maybe, say, a Kleenex box instead, and we send it off, we can see the Kleenex box move. This thing stops early because the Kleenex box helps to take away its momentum. It removes the momentum. And when the momentum goes to zero, it stops. But how does the Kleenex box take away the momentum? Through impulse. That's where that comes in. Because the Kleenex box applies a force to this, right? Much like how when we were pushing on walls or talking about moving things with force, we were applying a force then. This Kleenex box is trying to apply a force back on the marker to stop it from moving. Now, you'll notice, of course, that for every acting force, there's an equal and opposite reacting force. So this acts on this, trying to push it this way. This one acts this way, trying to push it to stop. Now, you'll notice, of course, the Kleenex box moves. Why? Because it's not very well attached. If I switch back to the marker box, barely moves at all. Because it's got a nice rubber padding, it increases the friction, the roughness between the surfaces, as a reminder. So what we're looking at here is that impulse represents the effort to oppose or to remove momentum from a system, but it's also how I add momentum. When I move this object and I set it going, I give it momentum by applying an impulse. I use my hand to give it a force over a certain amount of time. And I can do a very big force in a short time, boom, by setting it off. Or I can do a small force over a long time, where I constantly push it. Hard to do with the roll of tape. So what we see is that the same force two different forces can give the same momentum depending on how much time I take. What do I mean by that? Well, let's take an example. Let's say that in order to push this roll of tape, I use, let's say I use 5 newtons of force. And if we remember here, we said that the tape had 2. Okay, so this over here is a 2 for its impulse. Right? And why is it 2? Because I want to keep this 2 over here, because that's what I end up with, and I'm saying that I'm using impulse to add momentum. Well, what time do I have to apply my force in order to make that work? This one's not going to be a nice round number, so we get out our trusty calculator. What do we get? Well, 2 divided by 5 equals 0.4 seconds. So if I have this roll of tape and I push it for just under half a second with 5 newtons of force, it will be moving with 2 kilogram meters per second of momentum. So my muscles give this momentum, setting it to go. If I push longer, it would go with more momentum. Okay, but let's say I wanted to keep the same momentum, but I was feeling particularly lazy, right? I didn't want to push with 5 newtons of force. I'm going to push with less. I'm going to push with half a newton. I'm going to push with 0.5 newtons of force. Well, I still want the same overall momentum, right? So I'm going to take a look at that and go, okay. 2 divided by 0.5 equals 4 seconds. So if I push with only a fraction of the force, I have to push for longer to make it go. So this might be why, for example, what's a good example here? Oh, if you're on a swing, right? You're sitting down on the swing, and someone else is going to push you, and up you go, and then back you come. Well, you've got 2 options when it comes to being pushed on a swing. Somebody could push you once really, really hard, or they could push you multiple times whenever you come back. And both those options will get you to the same overall speed, the same momentum, right? So you're, of course, big, super strong dad can really push it. Or maybe your older brother, who's not quite as strong, will come by and push once, and then they'll push again, and then they'll push again in order to get the same thing. Think of it like getting paid, right? You need $2 to go buy a $2 cheeseburger. Well, I can give you 2 loonies, or I could give you 8 quarters. All of them get you $2. The question is just, how many coins do I have to give you? How many times do I have to apply that impulse to get the momentum? Now, impulse is also super important for another big thing, cars, right? A car moving along pretty quick is much like these rolls of tape that I keep rolling around. If a car has a long time to slow down, right? If it can just mosey to a stop after you hit the brakes, nice and leisurely like, there's no problems. But if a car has to lose all of its momentum very suddenly, it's a crash. And cars have a ridiculous amount of momentum. They're big. They've got a huge engine doing a lot of work. So as a result, if a car has to stop suddenly, it can do a lot of damage. What do I mean by that? Well, let's put these 2 equations together here. Let me show you how these work. Because as it mentions on page 68, impulse is equal to the change in momentum. What does that mean? Change in. We have that phrase from before. Change in means something in physics. Change in means this. Impulse, J, is equal to the change in momentum. So if I do that again, let's say J equals PF minus PI. Okay, so we're going to talk about a car coming to a stop. So the initial momentum is going to be some number, and then the final momentum is going to be 0, because we're going to stop. Okay, that's easy. So I'm just going to make this 0 and make it disappear. Okay, so we've now changed our equation to just this. Now, negative is just going to be direction, right? It's going to be stopping, so we're going to slow it down, so negative. Okay, that makes sense. So I'm just going to erase the negative just to make our lives easier. Okay, so J is F times T, and P is M times V. Okay, so let's start putting some pieces together. The mass of the car. Okay, so cars are pretty big. So we're going to say that this is 1,000 kilograms. The velocity of the car. Well, obviously you were following the speed limit, so we're going to say that you were going, what about 60 kilometers an hour? No, you were in a school zone. You, being a very responsible person, are only going 30 kilometers an hour. Now, 30 kilometers an hour, we're going to divide that by 3.6 in order to turn it into meters per second. We've got to work with meters per second for our calculation. So we're going to go 30 divided by 3.6, and we're going to get 8.33 meters per second. All right, so we're going to put that in here. So you're traveling along in your 1,000 kilogram car at the speed limit in a school zone. Very responsible of you. How much momentum do we have? Well, let's take a look. We take 8.33 times it by 1,000, and we're going to get a momentum. We'll write it over here. We'll get a momentum equal to 8,333 kilogram meters per second. Now that seems like a pretty big number, right? Well, now comes the hard part. You got to stop, right? Some tiny, tiny child is playing soccer in the field and they run out in front of the car. You got to stop. Now, you got two choices. You stop when you hit the kid. Please don't do that. Or you stop before you hit the kid. Much better option. Well, in order to stop, you need to make that momentum number go to 0. Well, as we see in our equation, in order to do that, I have to apply a force. And I need a certain amount of time. Now, for our purposes, let's say that the kid is so close that you only have half a second to stop. It's not a lot of time. So let's say that you only have half a second to stop. All right, so we're going to say that the time here is 0.5 seconds. So let's put this together. We've got a momentum of 8,333. Okay, so 8,333 kilogram meters per second. And that's going to equal F times 0.5 seconds. So I have only got 0.5 of a second to get all of this momentum to go to 0, because that's how I stop. Okay, so let's see. How much force do you have to apply? How much force do the brakes have to apply to the car in order to make this work? Divided by 0.5, the force of the car brakes has to be 16666.66 newtons. That's a big number. That's a pretty big number indeed. So now, here's where the thing gets weird. You didn't hit the kid. Good job. But what happens if, say, I tell you that your bones break at 16,000 newtons of force? I make that number up. It's not really true. Your bones can take way more than that. But what happens if they did? Well, you look at the math here. The red number is bigger than the green one. So what happens is that you hit on the brakes, the car has to come to a stop. Well, you're moving in the car too, so your momentum has to go to 0. But if you have to experience this much force, you can only take that much force, you get hurt. Well, that's no good. You don't want to do that. So what can you do? There has to be something, right? People walk away from car crashes all the time. Well, there's a trick. And the trick is the time. If you stop in only a half a second, you don't have a lot of time, right? You're driving along and suddenly you go, and that doesn't give you a lot of time. You're going to crash. You're going to hurt yourself. But if we can make the crash take longer, then you'll be okay. Right? Because watch. Let's pretend, instead of taking 0.5 seconds, let's pretend we make it even just a little bit simpler. Let's say we make it take 1 second. Well, if it takes 1 second, this number isn't 16 anymore. This number is only 8,333. And that's way under the limit of 16. So if we manage to make the crash, the stop, I should say, not the crash, you didn't hit the kill. If we manage to make the stop take only 1 second, a half second more, you walk away a little rattled with nothing broken. So how do we do that? Remember with the Kleenex box. And I take the roll and I roll it towards the Kleenex box. And I miss in this case, good job me. And it stops, but the Kleenex box moves. Because the Kleenex box moves, the collision takes longer. If I compare that to this, it doesn't move, so the collision is fast. The purpose of airbags in your car is so that way when your face hits the airbag slowly falls inward. Slowly. Half a second more is enough to keep you in one piece. So the way that you keep people safe in a crash is that you make it take longer for them to slow down. The same is true with anything. If you were to get shot, don't do that either. Man, look at this. We got such a dangerous class today, momentum impulse. If you were to get shot with a gun, ooh, well, what happens? If you get shot, the momentum of the bullet has to go to 0. If it does, it stops, and you want the bullet to stop. But if the bullet stops by hitting you, well, your body has to apply a force over a time in order to make that happen. If the time is very, very short, because the bullet is, moving very fast, the force has to be really, really big, you get hurt. In a slightly less gruesome manner, let's take a look at this again. You see it goes back and forth. What happens if I keep my finger here? And I got to do this just right so you guys can see it. Let's see. I don't want to do this. There you go. If I keep my finger here and I raise this up, if you watch, you can see that my finger depresses inward. My finger has a little give to it. My finger absorbs the momentum, and it can handle that momentum because it's not very big. And it also delays the strike. So my finger ends up basically being, instead of like this, it compresses inward. That's why we're spongy like that, because then we can grip things, we can delay things. We are basically covered in a giant hot air airbag by design. This is different from, say, bugs who have got a hard shell on the outside surface. So everything to do with momentum and impulse is about making the right choice about how much force in how much time. Another example, baseball, right? The ball's coming at me, I swing with the bat. The bat hits the ball goes flying. I give the ball momentum to make it fly. When someone else catches the ball, they take all the momentum away. It's the only way the ball will stop moving. But of course, getting hit with a baseball hurts because it's got a lot of momentum. And if it hits you, you got to stop it really quickly. So instead what they do is that you have a catcher's mitt. And you generally don't want to catch the baseball, in the face. Instead, you catch it in the hand. And when you catch the ball in the hand, what happens is the ball hits, boom, and your hand doesn't sit there perfectly still. Your hand goes backwards a little bit. It gives. And the purpose of that give is to make it so that way it takes longer for the momentum to be removed, which means you need less force overall, so it doesn't hurt as much. Okay, so that's the fundamental of momentum and impulse. Okay, you've got momentum if you're moving and you have mass, and pretty much everything that moves has mass. And if you take that momentum to 0, you stop moving. And you use impulse to give momentum, and you use impulse to take momentum away. And the big question is, how fast do you give or take the momentum? Do you give a lot in a short time, or do you give only a little bit over a long time? Sometimes you want one, sometimes you want the other, right? Like nobody would want to watch a baseball game where somebody like slowly pushes the ball through the air or just like gently nudges it, you know, like somebody playing golf and they just putt, putt, putt the whole way through. Also, nobody wants to be in a car crash where everything stops really quickly. You always want to take your time. You always want it to go slow. So there you go. A little bit about momentum. Now, after this, you guys can take a look. You guys have got some more practice you can do on page 70. Page 71, 72, 73 are the last bit of notes. I'll see about putting together a video on that right away. The last bit is about energy, because there's one little piece to this puzzle that doesn't quite make sense. If I let this go long enough, it stops. Why? But we'll save that one for the next one. So, give things a try, ladies and gentlemen, and I will see you on the next video.